Hey, so the fact that we called the last one single replacement was a big indication that there was another kind of replacement out there. If you had to guess what the next one would be called, if the first one was called single replacement, you probably would have guessed the next one was going to be called double replacement. Okay. So in double replace, that means two things replace. But what do they replace? They replace each other. They switch spots. I'll replace you, you replace me. So in our dancing analogy, we would consider this part of square dancing. Now the man left, change partners. Okay? So that means if you're going to change partners, that means you must have started off with a partner. And you're dancing with another partner, or somebody else who's got a partner, right? So you have to have two compounds as your reactants. You have to have partners already when they start. Because without a partner, then it'd be single replacement. Usually an aqueous solution. So aqueous solution, remember, dissolved in water. So, to give you an example, oops, that's the wrong stuff. We want to get the right stuff. Hey, so here I have two solutions. A solution of NaOH and a solution of FeCl3. So I pour in the NaOH. Nice clear solution. Can't see the NaOH because it's all dissolved. FeCl3 is also a clear solution. It's colored, but it's clear. It's an orangish color, but it's clear, just like Kool-Aid's got a color, but it's clear. Okay? So it's dissolved. The ions absorb some of the colors. And when I pour those together, this orangish clear liquid, hey, something happened? There's something here that's not one of these two. Hey, let's figure out what it is. Okay, what's the dark brownish orange stuff that's in here? What's that stuff? Well, we can figure it out from here. NaOH plus FeCl3. So they're going to change partners. So I think of it as the positive ions changing place. It would be equally valid to say the negative ions change place, but I pick positive because they always lead. Because the positive always leads. So the positive ion in NaOH is the Na, and in FeCl3 it's the Fe. It's going to be the first piece. And those are going to switch partners. So the Na that was next to OH is now going to be next to Cl. And the Fe that was next to Cl is now going to be next to OH. So I color-coded my two compounds so you can see where the pieces came from. Notice I did not bring the 3 over. That 3 is there to make it equal 0. That's about charge. I'll have to figure out how the charges work out on the other side. So I looked up sodium on the periodic table. It was in an alkaline earth metal, group 1A. It was 1 plus. Cl was a halogen, 1 minus. So 1 plus, 1 minus, that's right. OH, I looked up on the back of my periodic table. It's hydroxide. It's got a 1 minus charge. Fe. I went to go look up Fe, but periodic table's not going to tell me anything about the charge of Fe. Where I'm going to get the charge of Fe from is the other side. Okay. Cl was 1 minus, and it took 3 of them, so I have 3 minuses, so the Fe had to be 3 plus, and that's how I knew that was 3 plus. They used the reactants to figure out what the charge on the, because I'm not going to change what the charge is this time. Single replacement changes the charge, double replacement doesn't. Okay? Just changes partners. Okay? So when I do that, I'm going to have to put 3 next to OH, which means I need parentheses. So first I did what the name said, switch partners, double replacement. Then I used charges to figure out subscripts. Then my next step is to balance. So all I did was the crisscross, put that 3 there. Now to balance it, 1 Na on both sides, 1 OH and 3 OHs. I should put a 3 in front of NaOH to get my 3 OHs. That gives me 3 NAs, so I need to put a 3 in front of NaCl. And that gives me 3 Cls, which I wanted anyway. So now it's balanced. 3 NAs on both sides, 3 OHs on both sides, 3 Cls on both sides, and 1 Fe on both sides. So this is in pictures what we had. We had 3 NaOHs, right? 3 NaOHs, and 1 FeCl3. Color went Alaman left. Change partners. And the NAs that were with the OHs are now with the Cls. Okay, that leaves us with one question. What's the brownish orange stuff? Well, it's one of these two, isn't it? Okay, NaCl. We know what NaCl is? It's table salt, the stuff you put on your fries. If I put table salt in water, what happens to it? It dissolves. So what's the brownish orange stuff? It's got to be iron 3 hydroxide. Because we know it's not this. And it is not. It only made 2 things, and we know which one it's not. So if we know which one it's not, we know which one it is. So that brownish orange stuff is iron 3 hydroxide. Okay with how I can figure that out? Yeah. So we cannot use the activity series because one will always be on top and the other one will always be on the bottom, which means there's always be one on the bottom and one on the top. So one of the directions it'll work and one of the directions it won't work every time. Activity series does us no good. Instead, what has to happen is the products, you have to make a product that separates it from the solution, that stops those ions from being separated. We saw one of the ways it makes a solid. That brownish orange stuff is solid. Give it time, it's going to sink down to the bottom of that test tube. It's the ones that we use the down arrow for. We said we could use a down arrow if it made a solid. This is the one we use the down arrow for because that solid is going to sink to the bottom of the test tube. That is by far the most common one. It also will happen if it's a gas that bubbles out. These are the ones that they tend to use the up arrows instead of writing the letter gas. The letter G. Because it would make bubbles and they would leave. This one you're never going to see. You're never going to be able to predict. Okay. Third way is you make something that's not ionic anymore. You make something covalent. And it says usually water. You can expect it to be water. If something makes water, that water is no longer ions in solution, it's the water. It doesn't have a charge anymore. You've taken it out of solution. So the way you make water is you put together something that starts with hydrogen and something that ends with hydroxide. So when they swap, you end up with hydrogen hydroxide, which is water. And polyatomic ions don't change from one side to the other. So the polyatomic ion stays together. You might need multiples of it. You might need to put parentheses and a subscript outside, or you might need to get rid of the subscript outside the parentheses. But the polyatomic ion stays together. That's it. All we got to do is follow those rules, and we do a few examples. So for right now, we're going to assume all these reactions take place. Tomorrow, we'll start seeing how we decide whether they're going to happen or not. So calcium chloride and sodium hydroxide. Okay. Okay, I recognize it's double replacement because it's two compounds. None of ours before have had two compounds where we're supposed to be able to predict whether we're going to make. So the calcium and the sodium are going to replace each other, which means they're going to switch places. So the calcium won't be next to Cl, the calcium will be next to OH. And the sodium won't be next to OH, the sodium will be next to Cl. So I did what the name says. Notice I didn't bring the subscript for the 2 for the Cl on the other side, because that's there so that CaCl2 adds up to 0. Right? It's not a polyatomic ion. That makes it add up to 0. Okay. I'm going to write the formulas right. Well, Cl is 1 minus and Na is 1 plus, so that's the right formula for NaCl. OH is 1 minus. I looked it up on the back of my periodic table. And Ca is 2 plus. Those don't add up to 0, so I got to do the crisscross. When I crisscross, I need parentheses, so I have 2 OHs, not just 2 H's. So I've done step 2. Use charges to write the formulas. Now I balance. 1 calcium, 2 chlorines. So I got to put a 2 in front of NaCl on the other side. That gives me 2 NAs, so I got to put a 2 in front of NaOH, which gives me 2 OHs, which I wanted anyway. So notice I counted OH as a unit because it stayed together. That was the one thing we learned new on Friday. Okay. Let's kick it up a notch. CuCl2 plus K2S makes what? Well, the positive pieces are going to switch places. So the Cu was next to Cl. Now it's going to be next to S. The K was next to S, it's now going to be next to Cl. I don't bring either the 2's because those are about charges. Those subscripts are making it equal 0, they're not polyatomic ions. Cl's 1 minus off the table, K's 1 plus, that adds up to 0. I look at the table, S is 2 minus. I look at the table, what does it tell me about Cu? Nothing. I need the charge of copper. I'm not going to be able to get it from the table. Where I get it from is the reactant side. The copper is not going to change charge. So since Cl was 1 minus, and there was 2 of them, the Cl was 2 negative, so the copper had to be 2 positive. If I was going to write the name for that, that would be copper 2 chloride. Right? So it was 2 plus on one side, it's 2 plus on the other side. Now those add up to 0, so CuS is the right formula. So I've done my second step, got the right formulas. Now I balance. 1 Cu, 1 Cu, 2 Cl, so I got to put a 2 in front of KCl. That gives me 2 Ks, which I wanted anyway. These will balance fairly easy. If they don't balance easy, you've got a subscript wrong someplace. If you find yourself going in circles and just keep changing the same numbers again and again, you've got a subscript wrong someplace. Because if you get one of these subscripts wrong, chances are it won't balance. Make sense? Hey. So KOH plus FeNO3,3. Well, the K and the Fe are going to switch places. So the K is going to end up next to NO3. I keep the NO3, but I don't bring that 3. Make sense? I keep the polyatomic ion, but not how many there are. And then the Fe is going to end up next to OH. K is 1 plus off the table. NO3 I look up on the back of my periodic table, it's 1 minus. KNO3 is the right formula. I can look up OH minus on the back of my table, but I can't look up Fe. What's the charge on Fe? Well, I go over the other side. Since NO3 was 1 minus, I got 3 minuses, so the Fe had to be 3 plus. So if Fe was 3 plus on one side, it's 3 plus on the other. Then I do the crisscross, so I need FeOH3, OH3. So now all we need to do is balance this. Oops, my parentheses went away. 1K on both sides. One side's got 1 OH, the other one's got 3 OHs. So I should put a 3 in front of KOH. That gives me 3 Ks, so I got to put a 3 in front of KNO3, which gives me 3 NO3s, which I wanted anyway. Make sense? Okay, and probably the hardest one I could give you. H3PO4 plus CaOH2. Okay, the positive pieces are going to change place. The positive piece is the H and the Ca, and they're going to swap places. So the H won't be next to PO4 anymore. It will be next to OH. Hey, that looks familiar. What are you thinking it is? I got it, it's my job. Okay. And the Ca is going to end up next to PO4. Yeah. So the Ca is going to end up next to PO4. I keep the 4 on PO4 because that's a polyatomic ion. I don't keep the 3 on H because H3 is not a polyatomic ion. H is 1 plus, OH is 1 minus. You can see that that's just a bizarre way of writing water. Right. Ca is 2 plus. PO4 is 3 minus. So that's Ca3, PO4 2. So now I've got the right formulas. So I have to balance. And I'm going to make the table this time just to remind you about how beneficial polyatomic ions are. Look at all the O's and H's in this. You see H's and O's everywhere? Okay. When I balance this, though, I'm going to count H's, but I'm not going to count O's. I'm going to count PO4s, because that PO4 stayed the same on both sides. And then I'll count CA's, but I'm not going to count O's and H's. I'm going to count OH's, because that OH stayed together. Makes sense? So that's 3 H's, 1 PO4, 1 CA, 2 OH's on the reactant side, 1 H and 1 OH in water, 3 CA's, 2 PO4s. Well, I don't want to fix hydrogen or oxygen because they're everywhere. So I'm going to fix phosphate, PO4, by putting in 2 in the very front, because that'll give me 2 phosphates and 6 hydrogens. I know the hydrogen is going to change all the time, so I don't fight it. Okay. The Ca, I need it to be a 3 on the reactant side, so I put a 3 in front of CaOH. It gives me my 3 CAs, and it gives me 3 times 2 is 6 OHs. Now I'm down to the point where I have to fix O or H, and I have to fix them on the product side. And it makes sense to fix H, because H only shows up once. So I need 6 H's, so I'll put a 6 in front of there. That gives me 6 H's. And surprise, surprise, it gives me 6 OH's. And I'm balanced. Isn't that a lot easier than trying to count all the oxygens on both sides? And all the hydrogens on both sides? So that's all there is to it.